Hello everyone. There is no example in this class and there are quite a few clicker questions for Wednesday's class, but I would like to go over the free body diagram for the rotating amusement park ride on page 190. Okay, because this is a little bit confusing, and by just looking at the notes, it may not be clear enough, so I just want to make sure it's clear. Okay, so what we have here is, so we have a amusement park ride. So you basically get into a chamber, and the chamber is rotating as it's shown in the picture on the right side. It looks like it's rotating clockwise, and what you see right at the origin, where the X and Y intersects, is a person. Okay, so you can see the top view. You see the top view here, and on the left side there are two free body diagrams drawn for the same person, top view and the side view. And again, we will use XYZ. It's a three-dimensional case. That's why it's a little bit more complex, and there's friction. So you know that friction is sometimes somewhat troublesome. So we will discuss those. Okay, so first of all, this is going to be the rotation, but we are going to assume, so you get into the ride, you stay, and you just kind of lean your back to the wall or the chamber wall. And by just standing, do you kind of feel like a normal force, like a wall is pushing you at all? If it's not moving, not rotating yet, you don't really have that force yet, right? You're putting your weight on the chamber floor, but you are not really feeling the normal force from your back if it is not rotating yet. But we are going to think about the rotation, so there will be a normal force on the back of the person. When you're looking from the top, you feel that force going down along the y direction. That is the normal force, right? And if you look at the side view, that is, and compared with the top view, normal force is along the negative y direction, because we are saying positive y is upward. So if I use my y-axis on the side view, you can see that normal force is on his back, and it is to the right. Okay, so that's the normal force. And again, if there's no rotation, that normal force is kind of zero. And if the rotation gets faster and faster, you will feel that force is increasing. Okay, so we will discuss that soon. But let's complete the top view free body diagram first. Let's assume the chamber starts from 0. So you just get in the chamber, and then it will start speeding up and rotating clockwise. Then, at that instant, what is your intended motion? Think about Newton's first law. You have inertia, you have mass, right? So you are standing still. I'm looking at this case. You're standing still, but the chamber is kind of moving to the right? So that the rotation is kind of clockwise. But you want to stay where you are, because that's what the first law is, right? Object at rest wants to stay at rest. So your intended motion is actually to the left. So if the intended motion is to the left, when the chamber is starting to rotate, then the friction should be opposing to that intended motion direction, right? So we will feel a friction force, which is to the right. Let's call that F. I'm going to try to make that little F. And 2. That F2 is only non-zero in the beginning, when it starts like accelerating, when it starts from rest and then starts rotating, okay? So you don't have that after it gets into constant speed for the rotation and F2 becomes 0. Okay, so for the side view, again we have the normal force, We matched it with the top view, made sure of that. And what else do we have? So what they're gonna do is the floor is gonna drop. So we are right now stepping on it, right? But we are looking at the case when the floor drops, so we don't have a contact with the floor at all. So we don't really have a contact force from coming from our feet, okay? But we have the weight force, right? It is down along the negative z direction, as you can see it from the coordinate system. And what else do we have? Remember that on our back, we are leaning against the chamber wall, right? And because of that contact, we have the normal force. But there's also friction. You want that friction, otherwise you're gonna fall down because weight force is pulling you down, right? So again, intended motion is just falling down. Then opposing direction is gonna be opposite. This would be, again, little f1, that's a friction force. And there are no other forces acting on us, right? So this is all top view and the side view. So now that we know this, let's think about this case. This is we are the object and we are going through a rotational motion, right? Or the uniform circular motion, because the path is, as you can see, it's a circle. So when you see the path being a circle, even if it's not a full circle, but it is in this case, then the first thing it should come to your mind is the centripetal force and centripetal acceleration, okay? And if you remember that we covered centripetal acceleration earlier, we said that it always towards the center, right? So if this is the center here, the person is accelerating toward that direction. That is the acceleration, the only acceleration we have, okay? And that centripetal acceleration magnitude is given as v squared over r. But this acceleration is opposite to the positive y direction, so it's along the negative y direction, okay? And do we have any other accelerations if we consider the rotation of that chamber is constant? Okay, so we don't really have f2 anymore. We're gonna set f2 to 0 because it already started its motion and it reached a constant speed. However, again, the velocity is changing because velocity is tangent, so that's why we have that centripetal acceleration towards the center of the circle. So what I want you to see here is the only acceleration that exists when the person is right at the top here is downward acceleration along the y direction, okay? So knowing that, let's just start with writing our y component of Newton's second law. Sum of Fy is equal to May, and for the left side y direction, I'm looking at my free body diagrams and I have top and side view, both y-axes are here, so in each case they should match, and the only force I have is the normal force. And as you can see, it's along the negative y direction, so it takes a negative sign and it becomes negative n, and there are no other forces along y direction. That is the net force, okay? So centripetal force is not something that you show on the free body diagram or on the left side as the forces, but what this tells me is the normal force is the centripetal force in this problem, okay? So we just need to identify what force is causing the rotational motion, the uniform circular motion. In this case, it is the normal force. So that's what we have on the left side, and on the right side we have the mass. And remember that acceleration magnitude is v squared over r, that's the centripetal acceleration. But again, that is also negative because it's along the negative y direction, so it's going to take negative v squared over r. From this, negatives will go away and we will have mv squared over r as the normal force. Now we're gonna go and try to get some relation. So as an engineer, if you're designing this, you want to relate this to the coefficient of friction. and how it is related to the velocity and the radius, so you can design this thing, right? So let's just look into more things then. Let's introduce friction. Again, F2 is now 0, and I'm going to focus on F1, so I'm going to focus on the z direction. Let's write down sum of Fz equals to, fix that, MAZ. What are the z direction forces? There is positive direction is along F1, so it's F1 is positive, minus weight force is downward, but upward is positive z on the side view free body diagram. And what is the acceleration along z? The person is not moving at all, so the acceleration is 0. So F1 is the weight force. But what is F1? So this gives us F1 equals to the weight force, right? Or mg. We will get back to this. What is F1? So let's just kind of think about a case. If F1 is, if the object is on the verge of moving, and as a designer, as an engineer, you don't really want that happen, that's the extreme case. But it is a nice case so that we can get the relation. If the person is on the verge of moving, then this friction would be static maximum. First of all, the person is not moving, right, relative to the chamber wall, so it is going to be static friction for sure. And if you are looking for the on the verge of moving, then F1 will be equal to mu s times n. So we already had n, so I'm going to use that definition and plug it in here for this n. And then we are getting F1 to be mu s mass times v squared over r. We also know that F1 is mg, so these two are going to be equal to each other. So I'm going to say that F1 is also mg. Then what I'm getting is masses are going to go away, which is interesting, right? Because it tells you that the mass of the person does not have any effect on this. So you don't have to worry about the person's mass, but if you want to figure out the relation between the velocity or the radius of the chamber, you need to think about the gravitational acceleration, which is constant, right? And it is also related to the static friction coefficient. So this will be the relation. So like using this, again, you can figure out what you want, and again, just kind of as a designer, expect the worst and don't make this mu s too high. Maybe some people are wearing like some silky clothes or some less friction coefficient material, so that you can make sure that when the floor drops, they don't fall, right? Okay,